So, okay, time to start. Good morning, good afternoon, good evening, depending on what is your location. Welcome to the webinar on visible light communications, its principle and research towards 6G networks, organized by the networking channel. Our speaker today, if this thing moves forward. Okay. Our speaker today is Dr. Domenico Giustiniano from IMDEA Network Institute. We are colleagues at IMDEA Network Institute. I am Marco Ajmone Marsan. And I asked Domenico to speak about visible light communication, which is an emerging topic. Domenico has been doing research on this domain for a number of years. He has both the experience of a researcher and some entrepreneurship experience, because he has founded a startup that is active in the domain of visible light communications. So he will tell us both about the state of the field and about his startup and the commercial applications. Just 2 words to say that Domenico got his PhD in Rome, from Roma Tor Vergata, under the guidance of Professor Giuseppe Bianchi, that many of you, I guess, know. And after that, he worked in several different places: ETH, Disney Research, Telefonica Research, a very interesting background. Then he joined us in IMDEA Networks Institute, where he is doing very interesting work. So before leaving the floor to Domenico, let me just mention that you can enter your question at any time on the Q&A tool of Zoom, and at the end we will go through the list of questions and provide answers. There is also a possibility for a post-webinar interaction over the Slack tool. And you will find the instructions how to use this over your within the chat, so that there will be this kind of information. I don't want to use any more time because it's much more interesting to listen to Domenico. So I stop here and I give you the floor, Domenico.
Thanks a lot, Marco, and to everyone that is joining today. Let me see if I can go to the slides. I have what's the bar? Oops, sorry, some slight issue with that. I'm sorry. Is okay, so some issue with the opening, but okay, now it's here. So let me also move this away. Oops, it can doesn't work. Sorry about that. So today I'm going to talk about the research we've been doing in my group at IMDEA Networks, as well as the basic principle of visible light communication technology. Before we start, I would like to give a brief overview of IMDEA Networks, a public research center located here in Madrid, which is internationally recognized thanks to our publications in top conference, as well as the knowledge transfer and spin-off patents and standard. IMDEA is has very international diverse profile of researchers with more than 20 countries. The group where I work is the pervasive wireless system group that does a lot of research on several topics and focusing a lot on the system research side, so with experimental work. And this is also linked to the group website. So the principle of today's talk is in 3 parts. Is the principle of visible light communication. The second part it will focus on our effort to design an open source platform for research in visible light communication. And the third one we'll look at what we've been doing in the last year toward the 6G network. As mentioned already, there is a Slack channel, so feel free to post any question there. And after the talk, it will be great to answer to any question. So let me start with the principle of visible light communication. Light is everywhere. This is in the indoor environment. It's in the phones, in the cars, in the traffic light, this light is complementing the natural light and is making our life possible in new ways and forms. But what is visible light? I'm sorry for the I can't remove the bug. What is visible light? Visible light is a component of the electromagnetic spectrum that stimulate the photoreceptors in the human eyes. That's what we see as visible light. And in terms of electromagnetic field, it's the component of the spectrum going from 3080 terahertz to 780 terahertz. So it's quite a large amount of bandwidth if you can compare it to traditional radio frequency communication. The key invention for ubiquitous light was with the invention of the light emitting diodes. Light emitting diodes have been developed in several forms, from infrared to green light, but it has been quite a challenge to develop blue light. Then we developed the blue light. Finally, you could get all the spectrum of visible light. And so this was developed in the early 90s and by many shops in mid 2000s. And thanks to that, light has become ubiquitous, and we have recognized this. This has been recognized to the Nobel Prize in Physics to the invention of this technology. In terms of its impact on our daily life, this is dramatic, as prior technologies were able to provide a conversion only 4% from electricity into light. And now with light emitting diodes, it's more than 80% of efficiency. And the duration of this technology, the emitting the luminaires went from 1K hours to tens of years. Now the LED have been the trigger to visible light communication. In fact, thanks to the principle of visible light communication is to take a light emitting diodes and turn it on and off to transmit data. And in the simplest form, you can associate a bit 1 to the presence of light, a bit 0 to the absence of light. So for instance, in the picture, we show this pattern where we have bit 0, no light, and then bit 1 presence of light, and so on. And a key component of this technology is that it can be done much faster than any prior technologies. So fast that it allows to communicate a speed that allows for data transmission and enable several applications. A key component in terms of enabling this technology is the linearity. Linearity is key for designing any modulation and demodulation schemes. And that's also the case with light emitting diodes. So if we have two components, of course, in transmission scheme. We have the transmitter and the receiver. On the transmitter side, what it's used is density modulation. In simple terms, it means that the current is changed on the LED, and this results in linear changes in the optical power, which is number of photons which are emitted. So I increase linear input current and equal increase the amount of optical power. The same happens on the receiver side, where components like photodiode, cameras, and so on are used. And here we take the envelope of the received signal, and this signal is proportional to the receiver optical power. So in total, we have a system that is linear both on the transmission side and the reception side. Given this very brief background on how this communication possible, in the next few slides, I would like to present what are the main advantages of these technologies and the main misconception of the technology. From the, let's say, the positive side and the properties, let's follow what is Lambert and Cousin law, which provide well-defined directionality in terms of transmission. And so this is defined as simple as proportional to the cosine of theta, where theta is the normal to a certain direction, and m is a coefficient that may cause narrower beams. So the order is the order of m, the narrower is the beam. So this is a very defined beam with a directionality which is defined by this formula. This means that they are naturally more secure than any radio frequency communication system which broadcast their signal. If you would like to do the same with radio frequency technology, you will need to design a very complex system, more complex than any light emitting diodes that are naturally directed. The other main property is that the visible light communication doesn't cross object walls and natural obstacles, and this again avoid the problem. We make the system more secure, as there are no eavesdropper that may listen to the communication. There are more properties. Another one, main one, is the energy efficiency. And this comes directly from the efficiency and from the LED itself. And we have been trying to quantify this a little bit in one paper, in a Connex paper a few years ago. So if you take want to understand what is the power consumed for communication, this is only marginal with respect to the one used for illumination. So on the optical side, so in the case, for instance, of optical communication, we measured only an increase of 0.7% of additional power consumption for the LED. So if the LED is on for illumination purposes, in order to enable us communication, we need only additional power of 2.7%. Of course, there is power consumed from the baseband as any other communication. So in the case of IoT applications, and in this case about 500 kilobits per second, we are in the order of 17% of increased power. And this, of course, changes depending on the communication rate that is expected, but it also changes with the type of implementation of the baseband. Given this main property, on top of this property, we have another one, which is the free spectrum. The International Radio Frequency Spectrum Regulation from ITU stops up to 3 terahertz in several countries, some other country 1 terahertz. Any frequency above that is free, and so this means that the spectrum allows for anyone to communicate without requesting a license. A small note also in terminology before I go to the misconception. There is sometimes the terminology Li-Fi. Li-Fi is networked visible light communication. Other times, especially in some standard, the word light communication LC is used, and especially with using cameras. And then finally, optical wireless communication refers typically to both visible light and infrared spectrum of communication. But in this talk, as much as possible, we'll simply refer to visible light communication, VLC. So given this property, we need to take with a bit of need to take carefully what we just said about the RF spectrum and the fact that there is it's a free spectrum. There is, however, some recommendation, for example, from Ofcom Switzerland that state that any VLC system shouldn't impose any issue in terms of electromagnetic interference. However, LEDs are typically quite low cost, and the more they get low cost, the more there is some leaked radio frequency signal. So this comes from the change of current in the basement. So if you see the picture here, so we have this visible light signal that is causing some transition, and this transition is what causes the transmission of leaked RF signal on the wireless medium. This is also depicted on the picture. So there are two options to address that: to have better shielding, which sometimes is not done because of higher cost. And then we have been investigating in a Mobiok paper recently another approach where we control the radio frequency interference, where we take an additional conductive loop connected to the basement, and we control it such that the additional radio frequency emission is in a ISM band, and so it does not disturb any equipment that is using some license band. So in this case, so the additional RF interference is at about 27.1 megahertz. Then, given that is the advantage, but then taking with a bit of consideration about the radio frequency emission leakage, now we move to the misconceptions that are typically in this technology. The first one is about larger frequency band and higher data rate. This is not really the case. So in one of the first slides, I mentioned the bandwidth of about 400 terahertz, which we just do the numbers as more than 10,000 larger than the radio frequency. However, this does not translate into a bandwidth in a transmission speed, which is 10,000 larger. The main issue is that light emitting diodes can only modulate the light intensity, meaning that you only can change the amount of photons, but you cannot control optical phase. Basically, this means that the different photons emit a different wavelengths. They don't have any fixed phase relation, and they cannot be controlled separately. And so, for instance, if we take two different LEDs separately, we cannot send light coherently like you may do with two different RF antenna. So there's been a lot of work for advancing physical layer scheme in order to address this problem. Indeed, there are work that show that fantastic data rate of 100 megabits per second up to maybe a few gigabits per second. We specialize in the light emitting diodes, also laser. This is not the topic of today. We will look at some other aspect of visible light communication. A few other misconceptions are the following three. The first one is that it's possible to communicate during daytime. One may say, but the light must be off. Yes, but you can turn it on for a very short amount of time and then turn it off, so that in average you see the light off. But since you turn it on and off very fast, this little amount of time when it's on would allow to transmit some data. Of course, the amount of data is lower than you may expect with an equal number of on and off over time. The second issue is flickering. There is no flickering, contrary to what you may expect, because the modulation occurs at very high speed. and that's filtered by the human eye. So anything which is about 200 to 300 hertz is easily filtered. So we just see a constant light, even if we are sending a lot of data. And the third misconception is that the presence of interference by sunlight. That's true only partially, only if there is a direct exposure to photodiode. However, most of this noise can be easily filtered out to some filter unless there is a saturation in the link itself. So in the last years, there's been an increasing number of papers and research on VLC. Here indicate more or less the research started. It's when the selectivity index has been available. 2004 and so on, and then around 2010 I started my personal journey with visible light communication that I will talk about in the next slides. And so there is an increasing number of papers as well as interest from industry, as you can see also from the patents. This concludes the first part of the talk. I will now talk about our effort for an open source platform for research in visible light communication, reminding us about the Slack channel. When I started my personal work, 2010 was while I was working at Disney Research Lab. The application we were considering were much different from the one at the time. As was mentioned before, there was a lot of interest in studying VLC as an alternative to other technology for high-speed communication, so with specialized LEDs and so on, and very complex modulation. We took a different direction and tried to understand whether this technology could be applicable to IoT, Internet of Things. In particular, we look at applications like toy-to-toy communication, where you may have only some very low power light emitting diode as a transmitter. And we look into this technology, also exploited the same LED as a receiver. This is also possible, changing the polarization of the LED. And so we come up with a very low-cost protocol, low power protocol that uses only a single LED for communication and reception. And later on, when I moved at IMDEA Networks, my main effort was to try to address the issue that at the time there was no open platform to boost experimentation and high entry barrier for anyone in the networking community to work on this field. So that's why rather than looking at high-end visible light, we say that when we look at low-end, low data rate for embedded system, I create a platform that may allow others to enter into this field. So we took an open source and open hardware approach, and we designed OpenVLC over these years to lower the barrier to entry visible light communication, and to build a community intersection between embedded systems and visible light systems. VLC is consists of a visible light communication and physical layer, which are implemented as a driver, Linux driver, so that we can easily interface it to the kernel. And then we have designed a firmware that was then communicating to the front end, which is the CAPE. Was for us a main milestone when we've been able with a breadboard load the code and be able to ping to devices. So the visible light was on yet another interface on the Linux system, which is like here VLC 0 with its own IP address and so on, thanks to the fact that we created our own driver, and the two nodes were able to communicate and ping between each other, so being able to both transmit and receive. We moved this forward to several iterations. Let me remove second this pen. So I want to show this brief video that where we show the video. Want to look at very high resolution. There is some glitch as shown in the video over Zoom. So here we show that there was this light bulb that was transmitting data and to a visible light communication receiver, and data was displayed on the screen. In this case, the data that we were transmitting was the temperature and the humidity. And then once we were moving away the transmitter from the reception, that the communication was lost. That's me 10 years ago. So over the years, we've been moving to different iterations of the board, 1.0, 1, 1.3, 1.4. At each iteration, we've been increasing the communication range and the data rate. Data rate is now stable at about 500 kilobits per second, mainly limited by the embedded board that we are using in the system. Now an example of what you can do with this data rate is shown in this other small video, where we have this transmitter here that is sending a video to a receiver on this other side on the right. And so there is the monitor on the left that is displaying the original video, the monitor on the right that will display the received video. So with a bit of delay, there is the video received on the receiver side. And let me go quickly to the video is still streaming. At a certain point, we block the video with a hand, and which should happen sometime now. Yes. So the video is blocked, and so also the video streaming is blocked. So there is a hand blocking the video streaming, and then the video is resumed after the connection is resumed once the optical link is enabled again. So in order to create such a system, we have been in the beginning delivered the hardware to interested groups, and which helped to create a new MAC protocol, new hardware design, different applications, and so on, other platforms that have been based on OpenVLC. The main challenge for us was the approach to take. One was to take an engineering approach, focusing on development. However, we focus on top publications, and the other was research-driven approach. So focus on high-quality research and improve the platform to fulfill the research objectives. So this has been our drive. That's also the reason why we never look at the very high data rate, which has never been my personal interest from the research point of view. And on the picture, you see how the board has been developed over the years. And to conclude the second part, in the next 3 slides, I want to give you 3 examples of papers where we used the board, and we applied that to our research, which consisted in the publication of 3 SMConnex papers. The first one, we using the board only on the receiver side. In particular, we used what is highlighted with 1 and 2, a LED as a receiver and a photodiode, and we deployed on here on what is called the receiver. With the idea that we have a car that is moving fast below this receiver, and this car is embedding some code, and as the car move, the information received varies. And in this scenario, the idea was to see whether we could simply use a source like a sunlight to then be the source for creating a passive communication system. And on the picture, it's me with my PhD student, Ching, now tenure professor at UDelft. a test were done with my car. In the second work, we've been using the board for a localization system where our idea was to consider a scenario where two cars, there is one car and a transmitter car, a receiver car, transmitter car with a light emitting diode, and then the receiver car receiving the information. And as there is a change of orientation in movement, this create two different shapes in terms of isocontour where the sinuous ratio is constant. This depends on the property of LED as a transmitter as a Lambertian source. And in this way, by crossing these two isocontour, we can identify what is the position of the relative position of one device with respect to the second device. And in this system, we've been modifying again the board, providing introducing sensors and introducing an additional interface to communicate the sensor to the receiver device, showing an example of the platform could be extended. And finally, in the third paper, we look at densification of lighting, how to use this densification to create new opportunities for communication. We know that the radio frequency networks are getting more dense to increase network capacity efficiency. However, in terms of light sources, they are getting more dense than radio frequency access point. So the problem we look at in this paper was how to maximize this system throughput by switching on and enabling only the light emitting diodes for communication that are needed based on the relative position of the target device. And we've been extending the board here in this work because for instance, we needed to find a way to synchronize the system in a very low-cost manner. So rather than synchronization through the network, which was too slow for us, we came up with the idea of synchronizing to the optical signal, which is depicted here in this picture on the bottom. In order to do that, was the first time that we used the firmware, the Beagle one for faster sampling rate. So this concludes the second part of the talk, and then I will go to the application for a 6G network. 6G is today in its very early stage. We are in release 19 of the standard, so it's still not 6G will start with release 20. So we didn't start yet, but there is also a lot of understanding of what is 6G. However, it's clear that 6G is not only about higher data rate. There is potential roadmap for visible communication 6G through different directions. The first is that VLC is already integrated since last year in Wi-Fi chipset, at least from the standard point of view. There is the 811 BB standard that allows existing Wi-Fi chipset to be extended with visible communication capabilities. However, one of the issues is that these early products are only viable for original equipment manufacturers, are not available for the user consumer yet. So we don't know really what are the capabilities in real conditions. And why this is can be said as a part of 6G, because Wi-Fi is already part of the 3GPP as a radio access technology independent from the cellular system, but that can be accessed by the cellular system itself through specific radio messages. And so by doing that, then potentially also visible communication front end may be accessed. A second potential direction for integration 6G is that optical wireless communication is listed in the ETSI technology radar that tracks the major technology trends. However, there is not yet an industry-specific group which would indicate already that VLC is in an early stage for 6G integration. There is also a third one, which is more of interest for activity in my group, is VLC for sustainable IoT devices. Sustainability is seems to have a larger interest in 6G. And in particular, the battery-free system and what is called in the ambient IoT in 3GP terms is a study item of release 19. So in the next slides, we'll focus more on ambient IoT, which is then how we hope to contribute to future 6G networks. Batteries have caused several issues in terms of the fact that they are based on lithium, which are difficult to extract. There are even few regions of the world, creating a lot of friction between different nations, and they also have a harmful environmental impact, as only 5% is recycled. The demand also keep increasing, for instance, because of vehicle cars, and there is the issue that in large IoT deployment, you need to change the batteries, which cause additional sustainable issues. And so one aspect is that if you see on the picture on the top, on the bottom right, the expected number of IoT devices over the years has been decreasing and decreasing. So when years ago, it was expected by 2015 1 trillion of devices, IoT devices. Then this forecast decreased to 50 billion, and then new estimations say 25 billion by 2025. And potentially one of the reasons for this decrease is that large deployment require batteries. So it's difficult to really deploy large networks considering batteries. So the question is whether we can use LED lighting for downlink communication in systems where they don't require batteries. And so we can consider scenarios like home office, greenhouse, vertical farms for this type of application. And here we publish several papers in the last years that where I will only touch some of them at a very high level. I want to present in the next slides why VLC can be a good technology for battery-free ambient IoT scenarios, and in particular 3 slides dedicated to this. The first one is that if we consider a visible light communication receiver like the one depicted here on the picture, we can have it with a very low cost approach, with for instance like with a solar cell and a comparator. And the alternative with there is a way also to have a passive radio frequency receiver that will detect the original signal. So the issue is that if we have an envelope detector within RF spectrum, it's very sensitive to any interference. So, for instance, you can see he depicted in blue the output of the envelope detector, and because of some radio frequency interference, the voltage increase. And the problem with that is that you have a wake-up circuit that depends on this trigger, and so you deplete a very precious amount of energy. While that's not the case with VLC receiver, I would say the Li-Fi, but in its networking terminology, why the signal is very constant, and is the one expected from a on-off pattern that which is the one that was transmitted with both medium. Another advantage for this in terms of harvesting energy, as light is homogeneous, so you can exploit that not only for dense communication deployment, VLC deployment, like I mentioned in the past, dense VLC, but also for harvesting energy uniformly. In the picture here we show an example of the light intensity in a normal office environment. where the light normalized value of intensity was much more constant with the light, as indicated in the blue, with respect to the dot, which is the RF signal, that of course depends on the distance with respect to the radio frequency sources, which are much more scarce. And finally, the third advantage that we see is that we can receive data at a very low power budget using the VLC. We come up with an approach using a solar cell, both for harvesting, but also for communication. And the basic idea is depicted here on the left, where you have a solar cell. From a solar cell, you have a high-pass filter, a low-pass filter. The low-pass filter is the one that is connected to the harvester, is the energy that you harvest. The high-pass filter is connected to the communication chain, and is where the communication, the bit stream are received. In this way, after a simple comparator, we can then detect the incoming bit stream. And we've been showing that this approach is very energy efficient. So on the right, we show so the consumption bit, joule per bit, which is just a fraction of any other communication system. So this means that for battery-free scenario, this type of approach is very efficient. Then we'll be looking more carefully at the case of agri-tech scenario. This scenario, we have vertical farms, greenhouses, aquaponics, a different type of agri-tech markets. But overall, it's an ecosystem that with a value that has increased over 10 in the last 5 years. Because of the food scarcity, and they need to provide food closer to the people and the global challenges in terms of climate change, for instance. However, these type of solutions are strongly limited by the several issues. So it's sort of limiting the potential impact on this agri-tech market. One of them is operational cost caused by energy, illumination, water, labor cost, which is very intensive. So there is no water, maybe is not controlled at the plant level, is for the entire farm, for instance. And so there is not a precise way to control the environmental component, like how you optimize the illumination, for instance. The consequence of that is the low production of crops. And there is also the issue that there is no food regulation for sustainability that must be taken into consideration, so that it's not easy to become highly productive, considering also the need to follow this regulation for sustainability. So overall, so there is a picture on the bottom also show some more details in terms of energy consumption coming from light, heating, and cooling. So all this must be optimized to really have this type of agri-tech farms becoming smarter. Our approach is based on what I've been mentioning so far. So light is largely available in this type of environments, and it's there for the crop themselves. So why don't we retrofit this light to also provide communication? And so we send commands to devices which are battery devices, which are deployed close to the plants, and we say, of course, updates of firmware and so on, so to control these devices. And then we receive back sensing data from these battery-free unit devices. If you see this scenario, of course, we can leverage the fact that this large amount of light that is there for the crop themselves. And this means that, for instance, there is high luminance in this type of scenario. So, for instance, considering illuminance to 10,000 lux for lettuce, this is much larger than what you have in indoor environment, 500 lux, and it's a good fraction of what you have with sunlight, which is in the order of 100,000 lux. So this means that this large amount of light allow to reduce the size of solar cell that will harvest the same amount of energy just with a fraction of the size that you might have in a typical indoor environment. And that's of course great in order to reduce the overall size of the IoT devices. So these are additional opportunities. However, in order to integrate a battery-free visible light with and make it realistic, we need to integrate it with RF technologies, and there are two ways where we see this integration or between visible light communication and radio frequency technologies. One is an underlink communication, and the second on the backhauling, which I will briefly review. The first problem is that, so I've been talking about the downlink communication. For the uplink, it's very inconvenient to use VLC because it's more energy costly because and it doesn't make it's more directional, and for certain applications it's unpleasant. On the other hand, the radio frequency backscatter has been is a technology that has emerged in the last year. It is very low power and consists of reflecting existing radio signals in the environment, and it can be done at very low power. And in our work, we leverage these two technologies for battery-free IoT system. At a high level, we have VLC for downlink, radio frequency for uplink, as shown here on the picture. Well, we did more than that. So what we did is illustrated in this picture. So we have the lighting network, the battery-free IoT devices, and we transmit in downlink first data, as we've been doing in any other system. But then for the uplink, we send we send a special message in downlink to avoid the generation of the oscillating signal inside the battery-free IoT devices. So in this way, we offload the generation of this oscillator to the lighting network. And our idea is rather than a simple on-off signal for an oscillator to generate a chirp, which allows to communicate a longer range like you would have with LoRa. So the battery-free IoT device is mixing the visible light chirp with the RF carrier, and so it's generating a chirp, presence of chirp, absence of chirp that then can result in communication at very low signal-to-noise ratio. So yes, so then we alternate between the visible light packet and the chirp signal. We've been doing that, and we've been showing that we've been able to achieve communication in uplink at a budget of 3.8 microwatt, which if you want to give some number is about 3,000 lower than Wi-Fi. And this translates also in communication range, which are very large, 150 meters, with a normal carrier wave generator, which means that then you have the light that is like here in this demo, below on top of the IoT tag, but then the receiver may be much far away. So up to 350 meters of distance, and then so in this very short video we show that we can the signals that we receive through the technology that I presented to you are correctly received on the receiver side. So in summary, so we have this system with light transmitting a downlink and also energy to the battery-free IoT devices, and then we have uplink chips to the server, to the edge device. However, there is a missing component, which is the backhauling, and so we could consider current technologies, but they have several limitations in terms of deployment cost, flexibility, range, and so on. And so we come up with a solution that take a single Wi-Fi router, like a 211B, 211G or router, and is capable of allocating a single subcarrier of this router to a single access point. And we've been doing that to some reverse engineering, where the payload is such that we can control the amplitude of each single subcarrier. In this way, so the signal is transmitted to a specific Wi-Fi access point, and then translated into the optical domain. So what we do is depicted here. For instance, we take a subcarrier the subcarrier here, and this is allocated to a specific access point. And then we alternate, for instance, between the transmission symbol 16 and symbol 1, so that we generate amplitude shift king, so that which is equivalent to on-off king in optical communication. So we just change the intensity for this specific subcarrier. And this is very convenient for battery-free IoT devices, where we don't need the full bandwidth for a single live access point. Single subcarrier provide the sufficient bandwidth for a battery-free IoT devices. In this way, we can transmit simultaneously to several access points in the environment, just with this customized payload. And so we did a test in real environments to demonstrate this concept, the backhauling part called Lo-Fi, showing a scenario where the edge device was far away from the greenhouse, and then so downlink range with this backhauling technology of about 45 meters, which is sufficient then to control a single from a single edge device several greenhouses. So to conclude, we took this concept, we came up with an idea for a startup. We participated in a competitive EIT Jumpstarted program in Europe, and we won it. It's a very competitive program in the field. This encouraged us to continue, and so we created a company which has the objective to improve, increase the yield production, facilitate farming automation, a sustainable approach for becoming a smart agri-tech. And today, we are working on the product market fit, pilot testing our technologies, especially here in Spain, where we identified already several greenhouses interested, and we are in our first round for fundraising. And here also share the QR code of our website. So to conclude, I presented the fundamental concept of simulate communication, and I have reviewed the open source platform for research in OpenVLC that we have created in our group a bit more since and we started 10 years ago, and we've been developing since then, and looking also at some research outcome related to the border, like vehicular networks and dense indoor deployment. And I've been showing the recent focus on greenhouse applications, and show that it's essential to integrate VLC and radio frequency technology toward a sustainable 6G network. And thanks to my current and prior members of the group, here shown in some funny pictures. Thanks a lot.
Thanks, Domenico. Thanks, everybody, for joining. We just have 5 minutes. So we have 2 questions in the chat. The first one is, what is the use of IA integration in the battery, which I don't quite understand. I hope you understand it, Domenico. Otherwise, maybe the participant can elaborate a little more.
Yeah, I didn't talk about the AI today.
No, this is not AI, it's IA. Then we have another one who is asking if there are security concerns in the visible light communication system, if the attacker knows the communication policy.
It's a good question. I mentioned that security is improved in visible light communication thanks to the fact that it doesn't uh, mm, propagate through walls. However, I also mentioned that there is a leaked radio frequency component that comes from low-cost light emitting diodes. And this has been shown in the recent years, in particular by my former PhD student, Jing Wang, and the colleagues, of course, and that this leaked RF signal may be exploited by attacker to try to reconstruct some of the information on the visible light communication link. So it's very, very important to do proper shielding to avoid this type of problem. But on the other type of attacks are similar to the. So you need to be in the same room and the same environment. But it's more difficult to provide to attack if you are in the same so you need to be very close to the intended receiver.
Okay, thanks. Then there is a question on the Q&A tool, and referring specifically to one of your slides where you write, when the light should be off, optical power required for LED is not free. And there is a requirement, a request to explain this point.
Yes, I was not. I was quite quick on that point. So it's a very good question. So one of the main advantages of visible light communication is that if you consider indoor environment, we need light for illumination, and so if we want to do also communication, additional amount of light cause very little additional consumption. So I was presenting some number that in case of IoT applications, we will be considering is about 2% additional communication. However, if the light is supposed to be off, because for instance, there is sufficient sunlight, and we don't really need the lighting infrastructure for illumination. Creating a communication channel where we have a short period of time where the light is on, and then for the rest of the time it's off. So when the light is on, we need to turn it on, and this energy is only assigned to communication. So it's not there for illumination. So we don't see it because it's on for a very short amount of time. But from the communication point of view, it's an additional consumption of the system. So, but instead, if you in a typical indoor scenario where you want the light on for illumination, as I said, yeah, this comes almost for free.
Okay, last one. We have actually a three-part request on the Q&A tool, and the first point is what aspect of visible light communication is key for agri-tech? Is communication primarily for uplink? Question one. The second part is about the solar cell. Is the harvesting energy stored in a supercapacitor? And how long can it sustain it? Minutes, hours, days? And the third point is what kind of backscatter VLC surfaces were used or you are considering in your design?
Okay, on the there are a few questions. The one in terms of energy harvest, so the peculiarity of applying VSC to greenhouse is that there is a very large amount of energy, and so this is there for illumination purposes. And now what we have to do is to take existing LEDs that are there for these purposes, and then change the intensity. So we have, for instance, looking into collaboration with LED manufacturer for greenhouses to test some of those products and see which ones provide the features that we need. So the way I see it, VLC is a natural technology for greenhouse because by retrofitting the LED there, you can provide the communication in downlink. Now, the duration downlink is used for actuation and for updating the firmware. But then, as I was showing in the picture here, we also use the lighting network to control the uplink communication because we are flooding the generation of the oscillator, which is typically done in the IoT device, which is energy consuming to the infrastructure. So in this way, for the first time, both the baseband and also the radio signal are offloaded, and we have to create a communication system which can consume only 3.8 microwatt for communication. So in summary, VLC is used not only for downlink, but also for controlling the uplink communication to make the system more energy efficient. I hope I answered to all the questions.
Yes, it's also time to stop. So
Yes.
I wish to thank you, Domenico, with one of the comments that we received on the chat that I find very appropriate, that says, "Congratulations on the presentation, very enlightening."
Thank you.
And so thanks everybody for being with us. As you know, these events run twice a month. You have the possibility of interacting with Domenico on the Slack channel. Remember that there are the details on the chat. The next event, which is going to happen in 2 weeks, has not yet been announced, but it will be in a matter of days. So please stay tuned. You will receive information about what will be happening in 2 weeks. Thanks again, everybody. Thanks a lot, Domenico.
Thanks
Really
to everyone for
enlightening.
attending. Thank you.
And thanks, Tavrula, for setting this up. Bye-bye, everybody.
Bye-bye.